Hello everybody, I'm Josh. I was a computer science examiner, head of computer science in UK-based schools. Now I run a tutoring business where I've helped thousands of students to get better grades in computer science related courses. These series of lessons is to try and give you as little as possible to remember and still being able to get the best possible grades. And this is all going to be relevant for every single specification to do at A level, so Cambridge International, OCR and AQA. The topic of today's lesson is all to do with floating point. Now, floating point is one of those topics which, as a tutor, I always get asked to help students out with, so I thought I'd make a video on it. And we have to go through a couple of stages. We've got to be able to do fixed point. We've got to be able to do 2's complement, which is changing binary numbers into negative numbers. And then we actually have to do the floating point stuff. So let's get going. So fixed point is just essentially quite a standard binary conversion. Just all it is that we've got decimal numbers in there as well now. So if you're not familiar with that, this is how you do it. So we've got 4 numbers before the decimal point and 4 numbers after it. So here, I just put the decimal point in, and then I go 1, 2, 4. That's going to give me 6. And then this one over here is going to give me 0.5, 0.25, and you just keep halving it, 0.125. Now, for OCR and Cambridge International, you do not have a calculator in the exam. So I know you're probably like, I can do this. I don't need to. I can work this out in my head. You know, just take your time. There's no rush, is there, at the end of the day? Normally people finish the computer science exams really, really early, especially in the OCR one. I believe it's 2.5 hours. So, you know, just take your time. Guarantee you're going to get it right. So that gives you that. And then we just put the 6 and that together. So it's going to be 6.375, okay, for that fixed point number. Now, there is another method which you can use fractions. Either or will get you the marks because that's maths. So 1, 2, 4, 8. That's going to give me 8, 4, 2, so that's 14. And then this one over here, half, quarter. We add those two together. If you don't know how to add fractions together, that is a possibility. We've got to make the denominators the same. So times 2, so that's going to give us 2 over 4. And then now the denominators are the same, but we can add them. And in my opinion, I actually find this a bit easier to doing it in this particular method. So 3 quarters, okay? So it's going to be 14 and 3 quarters is our answer, okay? So that's fixed point. So that's step 1. Step 2 is being able to represent negative binary numbers. Now, negative binary numbers, the first step, I'm going to show you a method, which again, I think is probably the easiest way to use it. Let's say for the top number, it's going to be a 5-bit number. So I'm just going to represent 6 as a normal 5-bit number. So 2, 4, yep, so that's there. Okay, so just so that you know, 2 and 4, that's going to be 6, isn't it? Yeah. Then what I've got to do is to convert it into a negative number. I'm going to go from right to left and find my first one. Everything at this one and before it stays the same. So 1, 0. And then everything after it is flipped. So this 1 becomes a 0. And then the other ones go 1 and 1. Okay? 72. Let me show you how to do it with a slightly larger number. So we've got 64, 32, 16, 8, 4, 2, 1. And then all I've got to do, so I've got to put a 0 there. 64, take that away, that's going to leave us with 8. So it's going to be 0, 0, 1, 0, 0, 0. So that's 64 as a negative, as a positive binary number. The next thing that we've got to do is our method, which we're going to go from right to left, which is going to go there. 1, 0, 0, 0. Everything at it and before it stays the same. Everything after it is flipped. So 1, 1, 0, 1. So that's now negative 72 in binary. So now what we're going to do is we're going to have a little look at floating point. So floating point is all to do with trying to make the data as efficient as possible because memory isn't a finite resource. Now, to show you how this works, essentially, if we had like 3.4 times 10 to the 35, right? That's a huge number. And we've got to remember that memory isn't a finite resource and we need to conserve it as much as possible. And essentially what floating point allows us to do is for a huge number or a very, very small number with lots and lots of zeros in it, then what might happen is it's actually going to be more efficient to represent it in, you know, something similar to standard form, which you would have seen in maths. Now, A couple of keywords. This is going to be mantissa. This is a mantissa, this part, and this is the exponent. Okay, so what we're going to need to do is we just need to show what the example of this is going to be in binary. So if I make up a number, so 0, 0, 1, 1, 0, 0, 0, so we've got 6 numbers for the mantissa, and then it's going to give you 4 bits for the exponent. So let's just go 0, 0, 1, 1. Step 1. What we do is we convert the exponent into a normal number, which is going to be 1, 2. So that's just going to be 3. Okay. The decimal point is always between the first 2 numbers, and a positive binary number is in a positive mantissa is going to be 0, 1, and the negative mantissa will be 1, 0. So we put our decimal point there, and then what we do is we just go for moving it 3 places to the right. So it's going to be 1, 2, and 3. We redraw our number, so 1, 1, 0 there, and then we're just going to put 1, 2, and 4, and then we can see that this number is going to be 6. So that is how to do it for a positive mantissa, positive exponent. Convert the exponent, move the decimal point 3 places to the right, then once you need to, just convert it, and then you're all good. And then here we have got 6. The next one of what we're going to do is we are going to go for a positive mantissa, negative exponent. So again, I'm just going to pick a random number. So 1, 1, 1, and 0, 0. And there, actually, I don't want to give this one too much of a crazy number, because either we're going to get a really, really small number, but I'll show you in a second. So put it like that. And on this one, we're going to have a 1 at the front, and then we will go like this. Okay, so then this is telling us that it's a negative exponent because there's a 1 at the front. So the first thing that we need to do is we need to work out what the exponent is, but we need to 2's complement this first. So we're going to go here, 0, 1, and then we're going to go, so everything at it and before it stays the same, everything after it is flipped. That then gives us 2, doesn't it? So that's going to be negative 2. Now, if we think about 3.4 times 10 to the minus 2, what that does is that makes the number smaller, doesn't it? So it's the same situation in this one, actually, where what's going to happen is we need to make this number smaller. So we're going to put in a couple of zeros. This corresponds to the number. So if this was a 4, you would add in 4 zeros. This is 2, so we're going to add in 2 zeros. Then we just move the decimal point 2 places to the left, which is 1, 2. Redraw our number. And then all you've got to do is just convert it in normal fixed point fashion. So again, I'm going to use my fractions just because I find it easier. If you prefer using decimals, that's absolutely fine. So it's half, quarter, eighth, 16th. Now, an eighth is 2/16, so that's just going to be 2/16 plus 1/16, which is going to give us 3/16. Now, that's how we do it for positive mantissa, a negative exponent, which is where we do the 2's complement of the exponent, and then once you do that, you have to add the zeros at the front. Next one, negative mantissa, positive exponent, is where it's going to give us a negative value for the mantissa, so that's going to be 1, 0, 1, 1, 1, 0. Let's put it like that, okay? And then positive exponent is going to be 0, 0, 1, 1. Okay, now what we can do is we can work out our exponent, which is just nice and easy. That's going to give us 3. The decimal point is between here, but before we do that, we have to 2's complement the mantissa. So we're going to go move to here, everything at it and before it stays the same, everything after it is flipped, 0, 0, 1. Put that there. Move the decimal point 3 places to the right, 1, 2, 3. Redraw our number, 1, 0, 0, 1, and then put our decimal point in there, 1, 2, 4, 0.5, so then that's going to give us 4.5. Now, thing that everybody forgets to do is because we change this into a negative number, we have to put a negative there, so that's going to be minus 4.5. Big thing, you will lose a mark if you don't do that, so please make sure you do it. So for the negative mantissa and negative exponent, which is the final one, all we're going to have to do is put 1, 0, 1, 1. So I'll just make up another number, 1, and we'll go with, I'll try and do it so it's not too much of a crazy small number, So, yep, we'll go with that one. Okay. And then the negative exponent is going to be 1, 1, 1, 1. Okay. Now, we 2's complement this one. You can do it in you could actually 2's complement that one first. It's not going to affect the result, but 2's complement this one. And then everything at it and before it stays the same. Everything after it is flipped. So that's going to give us -1. The decimal point is here, so then we 2's complement this. So 0, 0, 1, 0, 1, 0. Decimal point is between there. And then what we have to do is, applying that rule when we had a negative exponent before, we're going to put another 0 at the front, move it a decimal place, and then we go 0, decimal point, redraw our number 1, 0, 1. And then we just, work it out as usual. Half, quarter, eighth, 16th. Add those two together, so that's going to give us 1/4 times 4, because we need to get the denominators the same, which is going to give us 4 over 16 plus 1 over 16 gives us 5 over 16. And that's going to be a negative number there. Now, just remember to put the negatives in there. So that is the final one on there that we have to do. That's all of the possibilities that could come up. Last little thing, which is just going to be a couple of knowledge-based questions, which is how can range and precision be affected by changing the size of the mantissa and the exponent? So if the range is increased, if the exponent is increased, so if the exponent is increased, you can represent a larger range of numbers. And then what you want to say is the precision is increased if the mantissa's increase. Underflow is, so it says describe underflow. So that is where the numbers are so small that you actually don't have the correct amount of binary numbers to represent it. And overflow, which you'll remember from binary addition at GCSE, is where you have too many bits and you haven't got enough space to represent it all.